As you know that we are discussing the unit thermodynamics, which relates heat of various systems to different functions. Today we are going to discuss importance of Gibbs-Helmholtz equations, conditions of equilibrium and criteria for a spontaneous process in terms of entropy change and in terms of enthalpy change. The third law of thermodynamics, the Nernst heat theorem and the determination of absolute entropies of solids, liquids and gases. Before proceeding further, you must recall what we have learnt in previous lecture. In previous lecture, we discussed physical significance of entropy, characteristics of entropy, free energy function G, work function or Helmholtz function A, variation of Gibbs free energy with temperature and pressure, Gibbs-Helmholtz equations in terms of free energy and enthalpy and in terms of internal energy and work function. In continuation, today we are going to discuss the importance of Gibbs-Helmholtz equations. Gibbs-Helmholtz equations are used to calculate the heats of reaction delta H or delta E when delta G or delta A at two temperatures are given. This point is made clear with the help of a problem. For the following reaction, N2 gaseous plus 3H2 gaseous giving you 2 NH3 gaseous, the free energy changes at 25 degrees Celsius and 35 degrees Celsius are minus 33.089 and minus 28.018 kilojoules respectively. Calculate the heat of reaction. Now, we can calculate the heat of reaction by using Gibbs-Helmholtz equation in terms of delta G and delta H. As you know that the equation is delta G is equal to delta H plus T d delta G by dt at constant pressure. Here we have G1 equal to minus 33.089 kilojoules, T1 is equal to 25 degrees Celsius, which is equal to 298 Kelvin. G2 is minus 28.018 kilojoules and T2 is 35 degrees Celsius, which is equal to 308 Kelvin. Now, putting these values in d delta G by dt at constant pressure, we will have d delta G by dt at constant pressure equal to 0.507 kilojoules. Now, according to the problem, at 35 degrees Celsius, delta G is equal to minus 28.018 kilojoules and T will be equal to 35 degrees Celsius, which is equal to 308 Kelvin. Now, putting all these values, we will have minus 28.018 equal to delta H plus 308 multiplied by 0.507 kilojoules. We will have delta H equal to 184.174 kilojoules. In this problem, we have studied to relate delta G and delta H with the help of Gibbs-Helmholtz equation. Similarly, you can do mathematical calculations to correlate delta E and delta A with the help of Gibbs-Helmholtz equation. Now, we will discuss the conditions of equilibrium and criteria for the spontaneous processes. First, we are going to discuss this criteria in terms of entropy change. The entropy of a system remains unchanged in a reversible change while it increases in an irreversible change. That is, sigma ds will be equal to 0 for reversible change and sigma ds will be greater than 0 for irreversible change. For a system with its surroundings, we can write ds system plus ds surroundings is equal to 0 for the reversible change. But ds system plus ds surroundings is greater than 0 for irreversible change, and combining the two relations we will have ds system plus ds surroundings is greater than or equal to 0. We are representing this equation as equation number 1, as we will use this equation for further derivations. If we assume the change in surroundings as reversible and surroundings evolve dq heat reversibly, then ds surroundings is equal to minus dq divided by T. And from the first law of thermodynamics, we know that ds surroundings is equal to minus dq divided by T is equal to minus dE plus dW divided by T. Here dE is the increase in internal energy of the system and dW is the work done by the system. From equation 1, we will get ds system plus ds surroundings is greater than or equal to 0. We can have ds system minus dE plus dW divided by T is greater than or equal to 0, or rearranging this equation, we will have T ds system minus dE plus dW is greater than or equal to 0. Therefore, we will have TdS system minus dE minus PdV will be greater than or equal to 0. This is our equation number 2. Now, we will consider different cases. In case 1, we are considering when E and V are constant. Here E is internal energy and V, you know, it is volume. In this case, dE will be equal to 0 and dV will also be equal to 0, and equation 2 will reduce to ds at constant E and V greater than or equal to 0, or we can say ds at constant E and V is greater than 0 for an irreversible change or a spontaneous change, and ds at constant E and V is equal to 0 for a reversible change, means at equilibrium. In case 2, we will discuss when S and V are constant. As entropy is constant, therefore, ds will be equal to 0, and as volume is constant, therefore, dV will also be equal to 0. On using equation 2, TdS system minus dE minus PdV greater than or equal to 0, this equation will reduce to minus dE is greater than or equal to 0, or we can say dE is less than or equal to 0. dE is less than 0 for an irreversible change or spontaneous change, and dE will be equal to 0 for a reversible change or at equilibrium. Now, we will discuss the conditions of equilibrium and criteria for spontaneous process in terms of enthalpy change. As we know that H is equal to E plus PV. On differentiating this equation, we will get dH equal to dE plus PdV plus VTP, or minus dE minus PdV equal to minus dH plus VdP. Putting these values in equation 2, we will have T ds minus dH plus VdP is greater than or equal to 0, or we can say dH minus VdP minus TdS is less than or equal to 0. At constant S and P, ds will be equal to 0 and dP will also be equal to 0. Therefore, we will have dH is less than or equal to 0. dH is less than 0 for an irreversible change or a spontaneous change, and dH is equal to 0 for a reversible change or at equilibrium. Now, the conditions of equilibrium in terms of free energy change. For free energy, you know that G is equal to H minus Ts, and as you also know that H is equal to E plus PV. Hence, putting this value, we will get G is equal to E plus PV minus Ts. On differentiating, we will get dG equal to dE plus PdV plus VdP minus TdS minus SdT. On rearranging, TdS minus dE minus PdV equal to minus dG plus VdP minus SdT. Substituting these values in equation 2, we will get minus dG plus VdP minus SdT is greater than or equal to 0, or dG minus VdP plus SdT is less than or equal to 0. At constant pressure in an isothermal process where temperature will also be constant, this equation reduces to dG is less than or equal to 0. From this discussion, the conditions for spontaneity and equilibrium may be summed up as: at constant internal energy and volume, ds is greater than 0 for irreversible process and ds is equal to 0 for a reversible process. At constant entropy and volume, dE is less than 0 for spontaneous or irreversible process and dE is equal to 0 for reversible process or at equilibrium. At constant entropy and pressure, dH is less than 0 for irreversible and dH is equal to 0 for reversible process. At constant pressure and temperature, dG is less than 0 for irreversible or spontaneous processes and dG is equal to 0 for reversible process or at equilibrium. For spontaneity and equilibrium, and these were derived by using first law and second law of thermodynamics. The first and second laws of thermodynamics have led to new concepts of energy content and entropy. The third law, however, does not lead to any new concept. It only places a limitation on the value of entropy of a crystalline solid. But before passing on to the third law of thermodynamics, we may consider briefly the Nernst heat theorem. This is an old generalization, but still has relevance as the forerunner of the third law of thermodynamics. Now, considering the Gibbshelmholtz equation in terms of delta G and delta H, delta G minus delta H is equal to T d delta G by dt at constant pressure. This is equation number 3. Richards, by measuring EMFs of a cell at different temperatures, found that the value of delta G by dt decreases with decrease in temperature, and therefore concluded that delta G and delta H tend to approach each other more and more closely as the temperature is lowered. Nernst, relying on this data, made an important suggestion that the value of delta G by dt approaches 0 gradually as the temperature is lowered towards the absolute 0, and this is known as the Nernst heat theorem. Now, according to this theorem, delta G and delta H not only become equal to each other at absolute 0, but also approach each other gradually at temperature close to absolute 0. Thus, the approach of delta G and delta H towards each other is as represented by the full line and not as represented by the dotted line. Mathematically, the theorem may be expressed as d delta G by dt at constant pressure, limit of t tending towards 0 is equal to limit of d delta H by dt at constant pressure when t tends towards 0 is equal to 0. This is our equation number 4. You know that according to second law of thermodynamics, d delta G by dt at constant pressure equal to minus delta S and d delta H by dt at constant pressure equal to delta Cp. This is Kirchhoff's equation, where delta S is the entropy change of the reactions and delta Cp is the difference in the heat capacities of the products and the reactants. From equation 4, 5 and 6, it follows that the limit of delta S when t tends towards 0 is equal to 0. This is our equation number 7, and the limit of delta Cp when t tends towards 0 is also equal to 0, and this is our equation number 8. Now, significance of these equations is that the entropy change of a reaction tends to approach 0 and that the difference between the heat capacities of the products and reactants also tends to approach 0 as the temperature is lowered towards the absolute 0. The Nernst heat theorem holds good only in the case of solids. By the use of Nernst heat theorem, now we will discuss the third law of thermodynamics. From the Nernst heat theorem, we know that limit of delta Cp when t approaches 0 is equal to 0. This means that at absolute 0, the heat capacities of the products and the reactants in solid state are identical. This leads to the suggestion that at absolute 0, all substances have the same heat capacity. The quantum theory as applied to heat capacities of solids has shown that heat capacities of solids tend to become 0 at 0 Kelvin. The Nernst heat theorem may therefore be written as limit of Cp when t approaches 0 is equal to 0. This is our equation number 9. Now, according to equation 7, we have limit of delta S when temperature approaches to 0 Kelvin is equal to 0. This shows that delta S becomes 0 at absolute 0. That is, the entropy change of a process involving solids becomes 0 at 0 Kelvin. In other words, the absolute entropies of products and reactants in solid state are identical. It is highly probable, therefore, that in the solid state all substances have same entropy at absolute 0. Planck therefore made the suggestion on analogy with the 0 value of heat capacity at absolute 0 that entropies of all pure solids approach 0 at 0 Kelvin, that is limit of S when T approaches 0 is equal to 0. This is represented by equation number 10. Now, this statement has led to the initiation of the third law of thermodynamics, which states that at the absolute 0 of temperature, the entropy of every substance may become 0, and it does become 0 in the case of a perfectly crystalline solid. In a perfect crystal at absolute 0 temperature, each constituent of the crystal must be at the proper crystal lattice point, and it must have the lowest energy. This means that this particular state is of perfect order, that is 0 disorder and hence of 0 entropy. Now, by using third law of thermodynamics, we can determine the absolute entropies of solids, liquids and gases. As we know that for an infinitesimally small change of state of a substance or a system, the entropy change is given by ds equal to dq by T, represented by equation number 11. If the change take place at constant pressure, then ds at constant pressure is equal to dq at constant pressure divided by T. This is equation number 12. Therefore, ds divided by dt at constant pressure is equal to dq by dt at constant pressure multiplied by 1 by T. This is equation number 13. Now, by definition, we know that dq by dt at constant pressure is equal to Cp. This is equation number 14. Therefore, ds by dt at constant pressure is equal to Cp multiplied by 1 by T. This is equation number 15. Now, at constant pressure, ds is equal to Cp dt by T. This is equation number 16. For a perfectly crystalline substance, the absolute entropy S is equal to 0 at T is equal to 0. Therefore, we may write integral of ds in the limits S is equal to 0 and S is equal to S is equal to integral of Cp by T dt within the limits T is equal to 0 and T is equal to T. This is equation number 17. Now, we have entropy at temperature T is equal to integral of Cp by T dt within the limits 0 and T. This is equation number 18. Now, St will be equal to integral of Cp d natural log T within the limits 0 and T. This is equation number 19. Here St is the absolute entropy of the crystalline solid under examination at the temperature T. The integral of equation 19, that is Cp d log T within the limits 0 and T, is evaluated by measuring Cp at all temperatures between T is equal to 0 and the desired temperature T. A graph of Cp versus natural log T is then plotted and then extrapolated to the absolute 0 of temperature as shown in this figure. The area under the graph gives the required value of entropy at temperature T. Since it is not possible to obtain the value of Cp at the absolute 0, heat capacities are measured up to as low a temperature as possible, usually up to 15 Kelvin, and the value at the absolute 0 is obtained by extrapolation. This method therefore consists in determining heat capacities of the substance under examination at temperature varying from approximately 15 Kelvin to the required temperature T. St is equal to integral of Cp d natural log T within the limits 0 and T. This is equation number 19, and equation 19 can now be written as St is equal to integral of Cp by T dt within the limits 0 and T star plus integral of Cp by T dt within the limits T star and T. This is equation number 20. In this equation, T star is the temperature between 10 Kelvin and 15 Kelvin. The second integral in equation 23 is evaluated from experimental measurements of heat capacities. Combining the heat capacity data with the enthalpy data on phase transformations, the absolute entropy of a substance, whether solid, liquid or gas, at temperature T can be determined. In every case, the start is made with the substance in the crystalline solid state at the absolute 0, when its absolute entropy is taken as 0. Then the total absolute entropy of the substance in the given state and at a given temperature is taken as the sum of all the entropy changes that the substance has to undergo in order to acquire the given state at the given temperature, starting from the crystalline solid at absolute 0. Now, let us revise what we have learnt today. Today, we discussed importance of Gibbs-Helmholtz equations, conditions of equilibrium and criteria for a spontaneous process in terms of entropy change and in terms of enthalpy change, the third law of thermodynamics, the Nernst heat theorem, and the determination of absolute entropies of solids, liquids and gases. In next lecture, we will continue with the application of third law of thermodynamics and residual entropy.